Hello students, today we're going to look at the states of matter, so a little bit of chemistry today. We are going to talk about the kinetic molecular theory. We'll talk about calculating calories associated with those changes in our states of matter. Now, as we go through this, at the end of the lesson, you should be able to describe the arrangement of particles and solids, liquids and gases, and then have some understanding of on a molecular level, how those different materials are able to change states of matter. The core vocabulary, everyone knows what solids, liquids, and gases are. I'm sure you've heard of what a plasma is. Kinetic energy, we talked about it in the first half of the year. And then we have some other ones that are very common. You know, when we're looking at freezing, melting, vaporization. A lot of these are familiar to you. But you have to have the background first before we can move on for the rest of this unit. All right, so we left off in the first section of the chapter where we were talking about the different branches of chemistry. All right, so chemistry, it's not just a physical chemistry and a biological chemistry anymore. There's a lot of different branches that we can break out into, but these different branches, there's no concrete definitive boundary in between them. So if we're looking at biochemistry, you're looking at chemistry in living cells. Well, you and I, we are predominantly carbon-based creatures, so that could get into some organic chemistry. And then if you're trying to describe the freezing and melting points of different compounds, well, that's a little bit of physical chemistry. So the branches do overlap. What you're going to have to do is be able to define what each one of those branches of chemistry would be defined as. So if you don't have all of those written down in your notes, I would really recommend you go back to Chapter 1, Section 1 and get those written down so that way you know what they are and you can easily recall those right out of your notes. So physical chemistry is going to be the predominant topic for our class this year. All right, so physical chemistry, we're describing matter in its present form and is in as many ways as possible. So if we're describing water, well, what's its freezing point? What's the temperature that it starts to boil from a liquid into a gas? What's the tenacity of a material? Is it the stretchiness? How stretchable? How much pull can we get from that before it breaks? The hardness. Is it a soft material? Is it a hard material? Density. How much matter is packed into a given space? These things go on and on. But one thing that you should take and get from these characteristics I'm defining is they are all based on the internal makeup of that material. All right, so if we're looking at the term that describes the internal makeup, properties based on the internal makeup of that material, what it's made up of, is called an intensive property. Or some textbooks, you'll see it written as an intrinsic property. So the way that I remember intrinsic is the word in, all right, so that is inside the makeup of our material. Now, if we were to look at, on the flip side of this, if we were to look at extensive properties would be like, mass and volume, things that have no bearing on the internal makeup of our material. If you have 5 pounds of water, well, that 5 pounds doesn't do anything to the freezing point or boiling point. Whereas intensive properties, it does depend upon the internal makeup. So these two terms, intensive, extensive, they do show up on our quizzes and tests. So you need to make sure that you know what those two things are. All right, let's move on here. If we're studying this physical science, you have to have an understanding of what matter is. Matter is anything with mass. And we're going to use our triple beam balances to actually measure our amount of mass of our materials. So our triple beams are going to be used quite a bit. We're going to look at the composition and the properties of it. So we'll look at the periodic table. We're going to be balancing some chemical formulas this year. You will need to become familiar. Now notice how I said that, familiar with the periodic table, not memorize the thing. All right, that will come with time. That's not something that you have to focus on. That will just be something that you acquire on your own. The more and more times that you see items on the periodic table. We're going to look at changes in composition, and probably the most important one to start off with is energy changes that are associated with anything in chemistry. When you're talking about a phase change, an ice cube melting, let's say some aluminum that is molten aluminum that is solidifying. All of those type of things. If you have a firecracker blowing up, all of those involve changes of energy. So that's what we're going to focus on right now. Now, this idea of these changes of energy comes from our kinetic molecular theory. I said that we had water that's freezing, we had molten aluminum that's solidifying. So the idea of these particles that are changing from solids to liquids or liquids to solids, that is associated with the kinetic molecular theory. Now, the term kinetic means particles in motion. So we have particles in motion. No matter what material you are looking at, your tabletop, there are atoms on that tabletop, and it's hard for us to see this because you can't see the individual atoms of that tabletop, but they are vibrating back and forth very, very rapidly. Okay, so those atoms that are vibrating back and forth, if we add more kinetic energy to it, what's going to happen to those atoms? Well, they're going to gain more energy. And you add more kinetic energy to it, what's going to happen? It's going to move even more. All right, so eventually, if you add enough energy to something, it's going to change from one state of matter to the next, from a solid to a liquid, from a liquid to a gas. Now, those three types of matter that I mentioned to you are the main types that you are familiar with: solids, liquids, and gases. But there's actually 5 types of states of matter. All right. The 4th type is plasma. I'm sure you've heard of that, but that 5th one, it's called the Bose-Einstein condensate. That's probably one that you haven't been introduced to at all, and we'll talk about that just a little bit in a minute. All right, so kinetic energy, these particles are moving around. Remember back in the physics half of the year, we had kinetic energy. Kinetic energy, in order for us to calculate how much energy there was, we had the formula 1/2 mass times velocity squared. Well, in the chemistry half, we're not going to use the joule for measuring how much kinetic energy something has. What we're going to do instead is we're going to use the term or the unit calorie. And these two things are interrelated. If you have 4.19 joules worth of kinetic energy, that's the equivalent of 1 calorie of energy. Now notice, if you put this in your notes, and this is going to show up on the test, this unit of measurement, notice that it is a lower case. You need to really make sure that you understand that 4.19 joules worth of energy is 1 lowercase c calorie. All right. I point that out because I know that you've heard of this term calorie before, but you might think of it as your food items. So what's the difference between a dietary calorie, which is written out with a large C like this? A dietary calorie is the equivalent of 1,000 lowercase c calories. So you might be asking yourself, why do we have this capitalized C right here? Well, if you take a look at your average candy bar is 300 dietary calories. All right. If we were to look at that in terms of chemistry, in terms of the amount of energy that's stored in those chemical bonds of that candy bar, you're looking at 300,000 lowercase c calories. All right, might freak you out when you're when you're trying to lose some weight and you're counting calories to see something that would be 300,000 calories. That and your paper on your wrappers wouldn't really fit that. So we use dietary calories. In this idea of measuring the average, now notice how I said that, measuring the average kinetic energy. See, if we're looking at your thermometers that we would be using, you would be measuring the average kinetic energy of those particles in that matter. All right. Now, the three scales that are used to do this, we have Fahrenheit. That's the one that we always use here in the U.S. But in science class, we are going to use the Celsius scale only. We are not going to measure anything in Fahrenheit. And then if we were to get into some chemistry even more, let's say we get into some gas laws, we'd want to look at the Kelvin scale. One side note, if we were looking at reading these off, a common mistake when people do this, you'd say 32 degrees Fahrenheit. We'd say 12 degrees Celsius. A common mistake that people make is if we change this to Kelvin, all right, our scale, and we were going to say 285. Sometimes people say 285 degrees Kelvin, and that's not right. When you're talking about the Kelvin scale, you just say 285 Kelvin. You leave the degrees off for that. So that's a little side note. All right, reference points that you must memorize. And I'm sorry, this is something that there's no reason why anybody shouldn't know the melting and boiling points of water. All right. When we're talking about water, we know that water is going to freeze at 32 degrees Fahrenheit. All right, 32 degrees Fahrenheit. If we're looking at water boiling, you have 212 degrees Fahrenheit. So we are not using the Fahrenheit scale. So what are we going to use instead? We're going to use degrees Celsius. And this is extremely easy. Water freezes at 0. Water melts at 0. We're looking at boiling. Water starts to change to a vapor at 100 degrees, and it starts to condense from a gas to a liquid at 100 degrees. The other item that I want to mention here in terms of reference points, absolute zero. Absolute zero is where, I said that your tabletop, those atoms are vibrating back and forth about a fixed position. Well, if we were able to stop that motion, remove every single last bit of energy from that particle, we would be at what's called absolute zero. It's where there's no molecular motion whatsoever. Now, we're not ever going to get to that point because you're always going to have some amount of energy to it. We can use lasers to slow the particle motion of atoms down, but you're not ever going to be able to get to absolute zero. Okay, but what would that be in degrees Celsius? Negative 273.15 degrees Celsius. So that's pretty darn chilly. All right, what are our 4 states of matter? All right, now I say 4 states, but in the beginning I said 5, didn't I? Well, I'll mention that 5th one at the very end. So let's start off with the one with the least amount of energy. Now these right here, every year I have people that get these things mixed up, and you have to, if you can't remember these, you've got to write these down. All right, the lowest amount of kinetic energy. That means that the particles are not moving around a lot. They're vibrating around slowly. All right, so if they're moving around slowly, they are going to have a fixed shape. If you have an ice cube, that ice cube has a fixed shape to it. If you take that ice cube out of your ice cube tray and put it onto the counter, all right, the space that it's in that ice cube, you take it out and you put it onto the counter, what happens to the size of your ice cube? It's still the same size. It doesn't change, right? So if you have anything that's a solid, no matter where you move it to, it's always going to have the same shape. It's always going to take up the exact same volume in its solid state. Okay, that's not going to change. And the reason why it's able to do that is because all of those atoms are packed into a lattice structure. You have over here, you've got this chain where they're all matching up right like this. All right. So if we were to take that block out of the beaker, oh, you see that? It's the same shape. Okay. So how can we get that solid to change shape? Well, you have to add kinetic energy to it. You add heat energy to it. If we take that ice cube, like I said, and let's grab this guy right here. All right, so we're going to copy this one, and we add some energy to it. If you add energy, you add some heat energy to it, what's going to happen to that ice? Well, it's going to change into a liquid. All right, well, that's an ugly liquid here. So we're going to put it inside of a beaker or a glass. All right, so here we have that liquid. Boop, there we go. It's close enough. All right, so we have that ice that changed its shape. Now, why did it change its shape? Because we added some kinetic energy to it. Now, the particles, there's still not a great deal of kinetic energy to it, but the particles here, they are vibrating around more and more because we've added kinetic energy to it. It's not enough that they separate and then they start moving around freely in the room, but we are able for them to slide and move past each other a little more freely. So that gives it a flexible shape or an indefinite shape. If you pour a glass of water into a large bowl, it takes the shape of the bowl, right, up to a certain volume. The amount of water that was in the glass that's dumped into the bowl, that does not change. Okay, the volume does not change, so that's a definite volume but an indefinite shape. Now, the other thing I'll point out here is that liquids cannot be compressed. Why would that be something that would be important to know? Is if you are driving in a car and you had little air bubbles in your brake lines, your car is going to feel mushy. The brakes are going to feel mushy when you put it on. You'll have to put your foot all the way to the floor. And why is that? Because gas is compressible. So you don't want to have any air bubbles in the line of your brakes. You want to make sure that it's only brake fluid in there because brake fluid is not compressible. All right. So we go to those gases. That gas that's inside of your brake line, well, first off, gases can be compressed. Gases can be compressed. So what can we get from that? Well, they're flexible in shape. And if they can be compressed, they're flexible in volume as well. If I take this lid right here and I add some pressure to it, all right, I push down on this, what's going to happen to the particle motion inside of there? Well, the particles are going to start to become more and more and more compressed, and we're going to have the same amount of air that's inside of there. All right, the number of atoms doesn't change, all right, but the shape of it will change and the volume of it will change. Not the number of atoms, but the volume and the shape will change. Now, how did we get to that gaseous state? We added even more kinetic energy. We added enough kinetic energy that they're able to break free of each other. Let's get to our fourth state right here. Our fourth state, a very high amount of kinetic energy. It's to the point where we're actually freeing off charges off of that material. So if you're looking at your fluorescent lights, you flip on the light switch. If you're looking at stars, you're looking at the sun, you look at a lightning bolt. All of those are examples of plasma. You have charged particles. So when we have the stars, when we have lightning, when we have all of these different forms of plasma, it is one of the most common states of matter in the universe, right? So since it is gas-like in nature, it's going to have a flexible shape and a flexible volume. So it's going to have an indefinite shape and an indefinite volume. If you're looking at, here's another example, neon lights. Neon lights would be an example of a plasma. All right, here we go. Let's look at a graphic of this. When we started off, we had the lowest kinetic energy, right? As we add more energy, it's going to change to a liquid. Now that material that has a definite shape and a definite volume goes to something that does not have a definite shape but does have a definite volume. You add more kinetic energy to it. Now these things no longer have a definite shape and they no longer have a definite volume. We add even more energy to it. We ionize those particles and we have a plasma. Okay. Now, I said that there was 5 states of matter, didn't I? The 5th state of matter, if we have absolute zero right here, absolute zero, that's where there's no particle motion, remember? No particle motion. Just before, right before it, few nanodegrees right before absolute zero, we have what's called the Bose-Einstein condensate. The Bose-Einstein condensate, no one really talks about it because in your science classes, because in order for you to form that material and even see that material, you have to have a lot of complex equipment. Solids, liquids, gases, and plasmas, those are all things that we can see on a daily basis. But the Bose-Einstein condensate, not many people, everyday people are going to come in contact with the Bose-Einstein condensate state of matter. Right? Maybe I'll throw a video on in the class, and I'll show you what that looks like. Okay, when we're talking about this flow of energy, our flow of energy is always going to go from a higher energy state to a lower energy state until things are balanced out. All right, when we get to our equilibrium problems, this is going to come into play. All right, so when we are changing these states of matter, we have to look at energy movement. All right, we have to have energy, and we're going to calculate that amount of energy right now. In order to calculate that amount of energy, you need this phase change diagram. Whether you get a picture of it, whether you have it in your notes somehow, draw it out, whatever you're going to do, you got to have this. All right. When we are changing from a solid to a liquid or a liquid to a gas, it doesn't just instantly, right as soon as, we're going to say that this is water here. Right as soon as it hits 32 degrees Celsius, 32 degrees Fahrenheit, we don't have ice and this is ice, we don't have ice that instantly changes to water, does it? All right, that's because we have to add a specific amount of energy to every single 1 gram of that H2O in order to get it to change from an ice state to a liquid state. All right, so I should put liquid right here. All right, so what is that called? What's that extra amount of energy called that is needed to change the particles at 0 degrees Celsius ice to 0 degrees Celsius water? That's called the heat of fusion. So I'm going to put this in here. So the heat of fusion. All right, we'll do some math and we'll talk about that later. All right, so we have ice that's going to heat up. We have ice that's going to melt. And then right here, water is going to warm up. And then all of a sudden, once you get to 100 degrees Celsius, water doesn't instantly change into a gas at 100 degrees Celsius. We have to go through another phase change. You need to get the particles of that liquid water excited enough that they change from this liquid state right here to a gaseous state right here. All right, now the amount of energy needed to change that is called the heat of, you guessed it, vaporization, because we are forming a vapor, right? There's specific values that are associated with that. So you have to continue to add more energy. And then lastly, if we add energy once it has been changed into a gas, and this would apply to you cooking your spaghetti on a stove. All right, some people, you want to cook your spaghetti or your noodles faster, so you crank up the heat. Well, what's the greatest temperature that water is going to boil at? Water is only going to boil right here. All right, so if water's maximum temperature is 100 degrees Celsius or 212 degrees Fahrenheit, you're not doing anything else to that temperature of your water. You're not going to increase the cooking or decrease the cooking time by cranking up the heat on your stove. If you want to get your noodles to cook faster, what we need to do is change the colligative properties. We have to add some salt into that water so that way it changes the boiling point of that water. By you adding a little sprinkling of salt into that water, you now change that water's boiling point to, say, 110 degrees Celsius. All right? So we'll look at the math of this in a little bit. So what is needed for us to do the math to change from one thing to the next? The first thing, not everything heats up and cools off at the same rate. So we have to look at this term called specific heat. Specific heat, the definition, is the amount of heat that must be absorbed or lost for 1 gram of that substance to change by 1 Celsius degree. All right, now if you don't like that definition, think of it this way. If you have a whole bunch of styrofoam balls that's filling a room, and you want to get from one side of the room to the next, all right, it's not going to take you a lot of energy to push your way through the styrofoam balls, all right? So small or low amount of energy. But if we take these styrofoam balls out of the room, and now we change the styrofoam balls to, say, bowling balls. The room's filled with bowling balls. Now you have to get from one end of the room to the next. Is it going to be the same amount of energy needed to get through the room? Or are you going to have more energy to get through that room? So you've changed the material. You went from a styrofoam ball to bowling balls. So if that material changed, the amount of energy needed by you to go through those materials is going to have to change also. So specific heat, each material requires a different amount of energy in order to raise the temperature of it. All right, so a couple of examples, and you need to make sure that you know what water's specific heat is. Now, when I say water, we're looking at just regular water. It's just H2O. It's not your tap water. It's not salt water. It's just regular H2O. The amount of energy needed to raise the temperature of water by 1 Celsius degree is 1. It's not a hard number to remember, guys. All right, now if we change that water to, let's say, ice, all right, ice, well, you're looking at different densities, right? The density changed. If you're looking at, let's say, gas, if you're looking at water in the form of gas, well, its density changed also. So do you think the specific heats for ice and gas are going to be the same? No, they're going to be different, right? Because they're different densities in the solid state and in the gaseous state. So they will require different amounts of heat energy in order for ice to warm up or cool off, or gas to warm up or cool off. A couple other ones here. You can see that brass, since it has a lower specific heat than water, which one's going to heat up and cool off faster? Brass is. It takes less energy to raise and cool it off than what water does. Copper, look at that one. Why are some of the best cookware copper? Because it heats up and cools off really fast. All right, so specific heat. We need to know what that is. Now, the unit for this is going to be C. We're going to use, C, well, not the unit. The variable for it is going to be C. Our unit for it is going to be calories, right? Remember energy, right? Kinetic energy per gram Celsius degree. All right, so if we're going to calculate the energy needed to raise the temperature of something, we're going to use this formula. Write this down in your notes. You're going to want to have this written down because it's going to come back. We're not going to do a lot of math in the second half of the year, but this is one of the things that you have to do since we're looking at chemistry involves a lot of changes in energy. We got to be able to calculate it, right? So what does the Q here stand for? That stands for energy. What does the C here stand for? The C is that specific heat that I just mentioned. The specific heat that changes from one material to the next. You'll never have to, if it's not water, have to memorize those. I'll give you those, but waters, you have to remember that. It's one, right? What do you think the M stands for? If we're heating something up, we need to know how much we're heating up. So that's the mass. And then if we're heating something up, if we're changing the temperature of it, the T stands for temperature. So I'm going to write this down. And when we're looking at our units of measurement, that Q, what is that Q going to represent? The calories of energy. So we have the calorie. 1 calorie is defined as the amount of heat energy lost or gained when 1 milliliter or 1 gram of water changes by 1 Celsius degree. So here, that is our change in temperature. This is our volume of water, and 1 milliliter of water is the same thing as 1 gram of water. And then right here, the C of water is our specific heat of water in the gaseous state. So specific heat of water, just plain old H2O, is 1 calorie per gram Celsius degree. So when we multiply all of these things out, the units of measurement, gram cancels with grams, degrees Celsius cancels with degrees Celsius, and the only thing that you're left with is our calorie. Now what we're going to do is we're going to have some calorie problems, and I already talked about the dietary calorie at the beginning. The only thing I didn't mention is if you have 1,000 of something, that's a kilo. All right, that should be something you'd be able to get. But what we're going to do now is we're going to do some problems in the class. I will put the problems as a separate video, but make sure that when you are looking at your notes, any of the information from our slides, that you get this stuff down because it's not going to go away. You have to know what these things are. All right, so we'll move on to our formula for or math for those calorimetry problems, and in a separate video. So until then, take care.